Classification of crystals into classes. Elements of symmetry. Part 2 of 3. Overview. This series is planned to comprise 3 parts. 1. Classification of crystals into systems, crystallographic axes. 2. Classification of crystals into classes, elements of symmetry. 3. Crystal forms in crystal classes, parameters. This is part 2 of 3. On the basis of symmetry elements, crystals are subdivided into 32 classes, unevenly distributed over the 6 crystal systems. In this video, the symmetry elements will be explained first, followed by describing briefly the properties of 8 representative classes covering all the crystal systems. At the end of this video, the interested viewer should be able to identify the class of crystal forms. Elements of symmetry. The symmetry is reflected by the presence of regular arrangement of the crystal faces and thus edges and solid angles with respect to a line as an axis, a plane, or a point as a center. These 3 kinds of symmetry elements, that is to say, axes, planes, and center, are used to group crystals into 32 categories called classes. It is to be noted that in this lecture, the focus is directed towards the symmetry of crystal morphology rather than the internal structure. In other words, the unit cell, motif, crystal lattice, etc. More details on the subject of crystallography may be found in the literature. 1. Axis of symmetry. An axis of symmetry, or axis of rotation, is an imaginary line passing through the crystal about which, if the crystal is rotated a complete revolution, that is 360 degrees, the appearance, in other words, the form as portrayed by the faces, edges, and solid angles, is repeated more than once. The type of the axis of symmetry depends on the number of times the appearance is repeated. If the number of repetition in a complete rotation occurs twice, the axis is twofold. 3 times, it is a threefold. 4 times, it is a fourfold. And if it occurs 6 times, it is a sixfold. Let us rotate this crystal model, which belongs to the tetragonal system, around the skewer stick as an axis. As we rotate the model, the appearance is repeated once, twice, thrice, and in the 4th times, as we finish a complete rotation, it returns to its original position. Let's repeat again. The form is repeated once, twice, thrice, and in the 4th times, it returns to its original position. So this is a fourfold axis of symmetry. Let us rotate this crystal model, which belongs to the orthorhombic system, around the skewer stick as an axis. Notice the front appearance with the red colored solid angle. As we rotate the model, this appearance with the blue solid angle is different. The form is repeated once. This appearance like the blue angle one. And now back to the original form in the 2nd repetition as we finish a complete rotation. Let's try again. Once, and twice, where it returns to its original position. Thus, this is a twofold axis of symmetry. 2. Planes of symmetry. A plane of symmetry, also known as symmetry plane or mirror plane, is an imaginary plane through a crystal that divides it into 2 halves, each of which is a mirror image of the other. The letter M is used as a symbol for the plane of symmetry. A plane of symmetry is called axial if it encompasses 2 crystallographic axes and perpendicular to the 3rd, and it is called diagonal if it encompasses 1 crystallographic axis and bisects the vertically opposite angles between the other 2. In the case of hexagonal system, A plane of symmetry is called axial if it encompasses 2 or 3 crystallographic axes, and diagonal if it encompasses 1 crystallographic axis, bisects the vertically opposite angles between 2 and perpendicular to the fourth. 3. Center of symmetry. A crystal has a center of symmetry if an imaginary line is passed from any point on its surface through its center and extended to the other side of the crystal. Then a similar point is found on that line at an equal distance from the center. This is equivalent to 1 bar or inversion. The easiest way to find out whether a center of symmetry exists or not is to lay the crystal on a plane surface. Then, if another plane surface appears on the top of the crystal parallel to the base, a center of symmetry exists. That is to say, when all the faces occur in parallel pairs on opposite sides of the crystal. Crystal classes. A summary of the properties of each of the subsequent classes will be filled in the following table. Note, the alphabetic symbols are more in use than the graphic symbols to describe the type of axis of symmetry. However, both are used here. 1. Hexahedral class. The name of this class is derived from the form with the highest number of faces, the hexoctahedron. This class has 13 axes of symmetry, 3 4-fold, 4 3-fold, and 6 2-fold axes, 9 planes of symmetry, 3 axial and 6 diagonal, and a center of symmetry. See the table. We are going to consider the cube as an example of this class and study its elements of symmetry in some details. Notice that the cube has 6 faces, 8 trigonal solid angles, and 12 edges. Axes of symmetry. If the model is rotated around a line connecting the centers of any 2 opposite faces, we can observe that this line represents a 4-fold axis. Since the cube has 6 faces, then we are going to have 3 4-fold axes as shown in the figure and the following video. Watch the front appearance of the cube. By rotating the model around the skewer stick as an axis, you can observe that the picture of the form is repeated 4 times. Thus, this is a 4-fold axis. Again, rotating the model, the front appearance is repeated once, twice, thrice, and in the 4th times it returns back to the initial position. So this is an axis of 4-fold. Each 4-fold axis of symmetry extends between the centers of 2 opposite faces. Thus we have 1, 2, and 3 4-fold axes. If the symbol A is used to indicate an axis of symmetry and a subscript is used to identify its type, then the symbol A sub 4 represents a 4-fold axis. Thus, 3A sub 4 indicates 3 4-fold axes of symmetry. Note that these 3 axes of symmetry coincide with the crystallographic axis. Upon rotating the crystal around a line connecting any 2 opposite solid angles across the origin, a complete revolution, the appearance of the form is repeated 3 times. Thus, this line represents a 3-fold axis. Since the cube has 8 solid angles, then there are 4 3-fold axes of symmetry. Each connects a pair of the solid angles across the origin as indicated in the figure and shown in the following video. Symbolically, this may be expressed as 4A sub 3. Watch the front appearance of the form. By rotating the model around the skewer stick as an axis, you can observe that the picture of the form is repeated 3 times. Thus, this is a threefold axis. Let's try again. Watch. 1, 2, and 3, where it returns to its original position. Each threefold axis of symmetry extends between two opposite solid angles across the origin. Thus, we have 1, 2, 3, and 4 threefold axes. By rotating the crystal around a line connecting the middle points of any two opposite edges across the origin, we can observe that the form is repeated twice in a complete rotation. Thus, this line represents a twofold axis. Since there are 12 edges in the cube, then the cube has 6 twofold axes of symmetry as depicted in the figure and shown in the following video. Symbolically, this may be expressed as 6a sub 2. Watch the front appearance of the form. By rotating the model around the skewer stick as an axis, you can see a horizontal edge, a face which is same as the front appearance, edge again, and back to the starting position. Thus, the picture of the form is repeated twice. Hence, this is an axis of twofold symmetry. Let us try again. Watch the front face with the black circle. One and 2, where it returns to its original position. Each twofold axis of symmetry extends between the middle of two opposite edges across the origin. Thus, we have 1, 2, 3, 4, 5, and 6 twofold axes. Planes of symmetry. There are 9 planes of symmetry in the cube. 3 of these are axial, each of which encompasses 2 crystallographic axes and perpendicular to the third. Each of the other 6 planes encompasses 1 crystallographic axis and bisects the vertically opposite angles between the other 2. They are diagonal planes. Note that each of the diagonal planes encompasses a pair of the parallel edges across the origin. Since the cube has 12 edges, then there are 6 diagonal planes of symmetry as displayed in the figures. Center of symmetry. A cube has a center of symmetry. This can be easily verified if we notice that when you put it on a table resting on a face, in any position there is always a face on top parallel to the base. 2. Hexahedral class. This class belongs to the cubic system. It has 7 axes of symmetry, 4 threefold and 3 twofold axes, 6 diagonal planes of symmetry, and has no center of symmetry. Let us consider the tetrahedron as an example of this class. This form has 4 faces, 6 edges, and 4 trigonal solid angles. It is in fact a triangular equal-sided pyramid. The tetrahedron has 4 threefold axes, each of which extends from a solid angle to the center of the opposite face, as indicated in the figure and shown in the following video. Let us consider the tetrahedron crystal. By rotating the model around a line extends between a trigonal solid angle and the center of opposite phase, we see that the form is repeated thrice. Thus, this axis of rotation is a threefold axis of symmetry. Let's try again. 1, 2, and 3, where it returns to its original position. Since we have 4 faces and 4 solid angles, then we have 4 threefold axes of symmetry. 1, 2, 3, and 4. Moreover, it has 3 twofold axes, each of which extends between the middle of the opposite edges across the origin, as shown in the figure and the following video. Let us consider the tetrahedron crystal again. By rotating the model around a line connecting the middle points of any 2 opposite edges across the origin, we see that this axis of rotation is a twofold axis of symmetry. Notice that the base of the triangle is up. Let us rotate the form. Here the base of the triangle is down. Now the form is repeated once, and the base is down again. Now repeated twice, where it returns to its original position. Let us try again. Once and twice, where it returns to its original position. Since we have 6 edges, then we have 3 twofold axes of symmetry. 1, 2, and 3. The tetrahedron has 6 diagonal planes of symmetry, as shown below. It has no center of symmetry, for there is no face parallel to its base. Instead, there is a point which represents the apex of the triangular equal-sided pyramid. 3. Dihexagonal class. This class, which is also known as pyramidal or diploidal class, belongs to the cubic system. It has 7 axes of symmetry, 4 threefold and 3 twofold axes, 3 axial planes of symmetry, and a center of symmetry. Let us consider the diploid as an example of this class. This form has 24 faces, 48 edges, and 26 solid angles. The diploid has 4 threefold axes, extends across the origin between 4 pairs of opposite trigonal solid angles. Moreover, it has 3 twofold axes that coincides with the 3 crystallographic axes. The diploid has 3 axial planes of symmetry, and it has a center of symmetry. 4. Dihexagonal dipyramidal class. This class belongs to the hexagonal system. It has 7 axes of symmetry, 1 six-fold and 6 twofold axes. It has 7 planes of symmetry, 4 axial and 3 diagonal planes. Moreover, it has a center of symmetry. Let us consider the hexagonal prism as an example of this class. This form is a combination of a prism with 6-sided vertical faces and a pinacoid perpendicular to the c-axis, forming the top and bottom of the prism. It has 8 faces, 6 of the prism and 2 of the pinacoid, 18 edges, 6 vertical and 12 horizontal, and 12 trigonal solid angles. This hexagonal prism has 6 twofold axes of symmetry, 3 of which coincide with the horizontal crystallographic axis. 3 of the twofold axes extends across the origin between the middle of the 3 pairs of opposite vertical edges, and the other 3 extends across the origin between the centers of the 3 pairs of the opposite vertical faces. Moreover, the hexagonal prism has one six-fold axis that coincides with the c-axis. The hexagonal prism has a total of 7 planes of symmetry. One horizontal axial plane encompasses the horizontal crystallographic axis, 3 vertical axial planes, and 3 vertical diagonal planes. Moreover, it has a center of symmetry. 5. Normal class of the tetragonal system. This class has a total of 5 axes of symmetry. A vertical 4-fold axis coincides with the c-axis and 4 horizontal 2-fold axes, 2 of which coincide with the horizontal crystallographic axis. It has 5 planes of symmetry, 2 diagonal and 3 axial, and it has a center of symmetry. Let us consider the tetragonal dipyramid as an example of this class. This form has 8 triangular faces, 12 edges, and 6 tetragonal solid angles. It has 5 axes of symmetry. 1 vertical 4-fold axis coincides with the c-axis, and 4 horizontal 2-fold axes, 2 of which coincide with the horizontal crystallographic axis. The tetragonal dipyramid has 5 planes of symmetry, 3 axial and 2 diagonal, and it has a center of symmetry. 6. Normal class of the orthorhombic system. This class has 3 2-fold axes of symmetry that coincide with the crystallographic axis. It has 3 axial planes of symmetry and has a center of symmetry. Let us consider the orthorhombic pinacoids as an example of this class. This form has 6 faces, 12 edges, and 8 trigonal solid angles. It has 3 2-fold axes of symmetry that coincide with the crystallographic axis. The orthorhombic pinacoids has 3 axial planes of symmetry. Moreover, it has a center of symmetry. 7. Normal class of the monoclinic system. This class has 1 2-fold axis of symmetry that coincides with the b-axis. It has 1 axial plane of symmetry and a center of symmetry. Let us consider the monoclinic pinacoids as an example of this class. This form has 6 faces, 12 edges, and 8 trigonal solid angles. The monoclinic pinacoids has 1 2-fold axis of symmetry and 1 axial plane of symmetry. Moreover, it has a center of symmetry. 8. Normal class of the triclinic system. This class has neither an axis of symmetry nor a plane of symmetry. However, it has a center of symmetry. Let us consider the triclinic pinacoids as an example of this class. This form has 6 faces, 12 edges, and 8 trigonal solid angles. It has a center of symmetry only. Now, let us try to test ourselves and find to which class are the following crystals belong. 1. Consider this form. To which system and class it belongs? Answer 1. This form has 3 equal axes perpendicular to each other. Thus, it belongs to the cubic system. It has 13 axes of symmetry, 3 4-fold, 4 3-fold, and 6 2-fold axes. It has 9 planes of symmetry, 3 axial and 6 diagonal, and has a center of symmetry since all the faces occur in parallel pairs on opposite sides of the form. Thus, it belongs to the hexahedral class. 2. To which system and class this form belongs? Answer 2. This form has 3 equal axes perpendicular to each other. Thus, it belongs to the cubic system. It has 13 axes of symmetry, 3 4-fold, 4 3-fold, and 6 2-fold axes. It has 9 planes of symmetry, 3 axial and 6 diagonal. Moreover, it has a center of symmetry since all the faces occur in parallel pairs on opposite sides of the form. Thus, this form belongs to the hexahedral class. 3. To which system and class this form belongs? Answer 3. This form has 3 equal axes perpendicular to each other. Thus, it belongs to the cubic system. It has 7 axes of symmetry, 4 3-fold and 3 2-fold axes. and 6 diagonal planes of symmetry. It has no center of symmetry since the faces are not occurring in parallel pairs on opposite sides of the form. Thus, this form belongs to the hexatetrahedral class. 4. To which system and class this form belongs? Answer 4. This form has 3 equal axes perpendicular to each other. Thus, it belongs to the cubic system. It has 7 axes of symmetry, 4 3-fold and 3 2-fold axes. It has 3 axial planes of symmetry and has a center of symmetry since the faces occur in parallel pairs on opposite sides of the form. Thus, it belongs to the dodecahedral class. 5. Consider this form. To which system and class it belongs? Answer 5. This form has 2 equal horizontal axes and the third vertical axis is longer than the horizontal axis. They are perpendicular to each other, thus this form belongs to the tetragonal system. It has 5 axes of symmetry, 1 4-fold and 4 2-fold axes. It has 5 planes of symmetry, 3 axial and 2 diagonal, and a center of symmetry. Therefore, it belongs to the normal class of the tetragonal system. 6. To which system and class this form belongs? Answer 6. In this form, the 3 axes are unequal in length and the A axis is inclined on the plane containing B and C axes. The B and C axes are perpendicular to each other, thus it belongs to the monoclinic system. This form, the monoclinic pyramids, consists of 2 pyramids, each of which consists of 4 triangular faces intersects all the crystallographic axes. It may also be considered as monoclinic pinacoids. This monoclinic pyramids has 1 2-fold axis of symmetry, 1 axial plane of symmetry, and a center of symmetry. Thus, it belongs to the normal class of the monoclinic system. I hope you have benefited from this video and gained an additional perception and analytical visualization when looking at crystal forms. The next video deals with the crystal forms in crystal classes parameters, with my compliments.